Okay, so we're doing our shortcut derivatives, right? These rules should all be memorized, but hopefully we understand them as well. If y equals c, like a constant, then what's the derivative?
0.
0. Because, right, so we're looking at like y equals 3, right? There's the line y equals 3. What's the slope of a horizontal line? 0. Remember, a derivative is giving me the slope at any point, right? So y equals mx plus b. What are we going to say about y prime?
Just remove the x.
So m.
It's just m, right? Remember, the derivative is a slope, right? The derivative is the slope, and this slope is the same at any point on the curve. So if we did this one with our limit definition, we would get exactly whatever the slope is. We're kind of moving up the chain here in polynomials, right? A number x plus a number x squared plus x plus it, right? So but we really want to talk now about x to the n. So this is called the power rule, right? And what's our derivative? It's n times x to the n minus 1, right? We're bringing down the power and then reducing the power. Why does it make sense that I'm reducing the power? Why does it make sense that I'm reducing the power by 1? By the way, you can definitely see that I'm reducing the power in the second one, right? It was x to the first degree to a constant, right? So why does it make sense that I'm reducing the power if you think about this secant line, the secant slope?
If you understand what the slope of a function is, then you know that you lose a power, because if you're
Yes,
thinking about
but why?
the direction of the increase of a slope, it's linear for, say, a polynomial, and it's completely flat if it's a linear function originally.
Well, I want to talk about this green box here. What is telling me that I'm reducing my power here by 1? Say it again, Markins.
Because of the division.
Yes, division by what though?
By the, is it like the x?
Yes.
X's?
Yes. If I'm dividing by x, right? Think about it. If I'm dividing by x to the first power, what's going to happen to my x in my numerator? It's going to lose the power.
It's going to get canceled.
Exactly. Nice, Markins. We got a couple more shortcuts that we'll be talking about. Some beautiful ones. We're going to just memorize them for now. I will prove them. So y equals e to the x gives me y prime is e to the x. This is a very special function. It's saying that the slope at any point along the function is the height of the function. Pretty unique. Pretty unique to have a function equal to its derivative. There are a few. If y equals ln of x, y prime is 1 over x. So this is a new list I'm giving you. If you look, remember I talked about those 2 blue pages at the beginning of the book. It's everything from pre-cal and before, and then there's like 4 pages at the end. I'm starting to work on the 4 pages at the end. We're gonna be memorizing as much of them as we can. There's some other beautiful ones. Y equals sine of x gives me a derivative of cos of x. Yes, it's hard to believe, but it's true. I will prove it. If y equals cos of x, the derivative is y prime equals negative sine of x. I've got a nice little shortcut to memorize this one. I'm going to draw a circle with an arrow going clockwise. Is that right? Yeah. And I put the alphabet on it. So A, B, C, right? So A, B, C. I don't want to sing. All the way H, I, J, K, L, M, N, O, P, Q, R, S, right? So you can see me writing the alphabet around the circle. And you see here, as I move from cosine to sine, I pass the negative. I pass the letter n. So derivative of cosine is negative sine. If I start at sine and go around the circle, I just get cosine, right? So if my function is sine, my derivative is cosine. If my function is cosine, my derivative is negative sine. So there's a nice list of our shortcuts, right? Let's do a quick tangent line with one of them, okay? Let's do one with sine real quick. I'm just avoiding talking about continuity, because it's so boring. I can't wait too much longer though. So let's do a quick tangent line with sine, the function sine, right? Everybody okay? Some of these are kind of strange, right? It's hard to believe, some of them. Afsoon, what's up?
So I just wanted to share my, because that works, for, derivatives of the trig functions, I just remembered that all of the ones that start with C have a negative.
Yes, even the arc cosine, even the inverse cosine, you're right. Yes, the cosecant, yes. That's a nice little, and it's related exactly to this. It's related to that, right? So all of those others. No, I like your thought. I like that. All right, here we go. Tangent line, quick tangent line, then we'll get on to continuity, right?
It's true because of the properties of co-functions in trig functions.
Odd and even functions, yes.
Yeah.
So sine, let's do a tangent line at, let's say, 7 pi over 6. So y equals sine of x. Y prime is cos of x. What do I need to get a tangent line? I need a point, right? And
the function.
I need the function. So to get a line, I need a point and a slope, right? So I need the point first. So let me get, right? So we've got x equals 7 pi over 6, right? Y equals sine of 7 pi over 6. Yes? This is the same as negative sine of pi over 6. And it's pi over 6, sine of pi over 6 is 1/2. Is this freaking anyone out? Anybody have trig issues? Abraham and
I was never a big fan of trig.
Well, it's time to become a fan. Because Calc 2 is jam-packed with trig, and I try and put as much in as I can, so I can make sure everyone's ready for Calc 2. Abraham and Udi, you guys, cameras are off.
I need to dig up my trig circle.
Yeah, I don't use a circle. So for me, I've got pi over 6, right, which means cut pi into 6 slices or make the whole pizza into 12. Find the 7th one, which is right here, right? 1, 2, 3, 4, 5, 6, 7. So sine is a y value, so I know it's negative now. But my reference angle is still pi over 6. So that's how I get this. And then sine of pi over 6 is 1/2, memorized, right? All right, so I've got my point 7 pi over 6. I've got negative 1/2 as my y. I still need my slope, and that's going to come from cos of 7 pi over 6. Of course, that is a positive cos of pi, a negative cos of pi over 6, which is negative rad 3 over 2. Again, I'm asking, and you can chat with me, I'll say nothing. Is this freaking anyone out? This trig stuff. Yes, you know, most likely no one else can see you nodding either, unless they've got a giant screen and the whole class is on there. But you want to, you want to look at that trig review in the book. It's either in chapter 1 or it's in an appendix. I think doing the Khan Academy trig course is good. It's free. It'll walk you through the whole process, right?
Professor, for reviewing for the test, you recommend us reading like the chapter 1 also or not? Because like
No, you took pre-cal.
Yeah, I took pre-calc, but like at the last I took pre-calc like more than 6 months ago.
I don't know. You got a formula sheet. I would put on, like some of you need that circle from trig. Put it on your formula sheet, right? You know, but, yeah.
The circle I don't need a lot because like since the beginning of pre-calc, I printed one big picture of that and I glue it on my wall. So I see
Yeah,
that
but I'm asking you all to not have anything on your wall.
No, not that. Like because I see that every day since like the beginning of pre-calc, I already memorized the circle.
Yeah, you might as well get the tattoo, but it's going to be painful. There's a lot of writing on that. All right, tangent line. Y minus a negative 1/2 equals negative rad 3 over 2 all times x minus 7 pi over 6. So y plus 1/2 negative rad 3 over 2 times x plus 7 pi rad 3 all over 12. Everyone with me? In Desmos, I could put it in right now. In your calculator, I can't, right? So I got to move that 1/2 to the other side. And get a common denominator. And there it is. When I'm doing problems like this, you're more likely not copying me, you're racing me. You're trying to get to a nice y equals mx plus b before me, right? And the more you can do that throughout the semester, the better. Just trying to, instead of copy, you're trying to do the problem as we go. Let's do a quick sketch here.
Professor,
Yes.
where is this located in the chapter?
It's not. This is chapter 3 I'm doing. But I'm trying to emphasize this tangent line, right? So when you're doing your new homework for Monday, you've got a bunch of, the first 2 problems is find the derivative using a limit, then graph it, and then come up with the tangent line. So the only thing I'm doing here is I'm not showing you how I'm getting the derivative, right? But the end process is still the same. I need a point, I need a slope. The point's coming from the function, the slope's coming from the derivative, and then I want to double check, I want to graph it, right? So y equals sine of x. I had the point 7 pi over 6. 7 pi all divided by 6, comma negative 1/2, right? Nice. Right away, I can already see I'm going to have a negative slope. So my cosine giving me that negative value was good. I can see I have a positive b value, right? I need a little bit of help here. For my tangent line, I had y equals negative square root of 3 divided by 2 times x. Is that correct? Yes. Someone give me verbal and can't look at you and type it at the same time. Negative rad 3 over 2 times x. Good. And then I had a 7 pi rad 3. Is that right? 7 pi square root of 3. Oops. Square root of 3 minus 6?
Yep.
Yep. All over 12. Boom. Tangent line. And again, I don't care about it crossing a second point. I wanted to make sure I'm zoomed in on the point of interest, and I see it's only hitting once there. Right. How we doing? We okay? Let's see if everybody's here.
That part's good.
4, nice. 4, 8, 18, 22, 23. Everybody's here. Awesome. First time. Oh, no, maybe the second time this semester. Everybody's here. It's good. You don't want to miss too many classes.
It's funny, you get better attendance online than in person classes, from my memory.
Yeah, I don't know. I mean, 8 o'clock is 8 o'clock, whether you're at home or, on campus.
Well, there used to be a lot of traffic on the road 2 years ago.
Yeah, that was my first COVID joke. Was I lost a lot of weight during COVID. I don't wait in traffic. I don't wait for the metro.
Yep.
Okay, here we go. Continuity. I think I gave this is a 2.4, section 2.4. Am I right about that? Here's my book. 2.4, and this is homework 5. Okay, so after today you should be able to do homework 5. Yes, 2.4. So first thing we have, it's obvious what it means to be continuous, right? It means there's no holes, right? If I'm walking on the path, there's no place to fall in, no place to fall off, right? So, but our definition, right, we'll say f of x is continuous at c at x equals c, if and only if. So meaning this is their equivalent. It's the definition. The limit as x goes to c of f of x is f of c, and that number, and that is a real number, right? This is the shortest way to say it. And our checklist, so we're doing 2 types of problems. We're going to either show something is continuous or not, or we're going to try and make something continuous, right? So we're going to try and show some piece of this fails for it to be not continuous, or make sure it works for it to be continuous. And our little checklist, right, is here. We're going to do 1. We're going to find f of c and make sure it's a real number, right? So show that f of c exists, right? If I get something like if f of c is infinite or undefined, no good, right away, fails, right? Step 2, show the limit exists. Show that the limit as x goes to c of f of x is real, right? Show that that exists. I'm simply saying by this bold R, meaning it's a number, right? Bold R means real numbers, right? And then step 3 is show that 1 equals 2. Right? Show that make sure those 2 results are the same number, right? Pretty simple. If any step of this fails, right, then it's not continuous, right? Does that make sense? Does everybody have a pretty good, I mean, this is the thing about calculus. Yes?
Purpose.
Yes.
Would a function like a exponential function, like going towards the right, that doesn't f to the c always exists?
Yes, but because I can't. Well, remember C is a number.
Right.
Right. So
So no matter what number, you can find a slope.
yeah. Well, now we're talking about continuity. We can find a limit. We can find a height. And that limit is the height of the function. So I jumped to derivatives. So wait for me on that thought about.
Okay.
Yeah, but yes, if this is 3 and this is e to the x, right? Then I've got the point 3 comma e to the 3, and the slope of the tangent is e to the 3.
Right.
So, but this is a different topic, right? We're trying to focus here on continuity. So continuity. Not only can I find the limit, but the function height is the limit. Okay? So I'm saying I'm not going to get the 0 out over 0 here, right? I'm not going to get a does not exist, right, if I'm continuous. There's no hole in the graph. There's certainly no jump discontinuity, right? I don't care about unbounded because it doesn't exist on the graph. It fails right away, right? Like if I'm looking at is f of x equal 1 over x continuous at x equals 0? No, right? It's obvious, right? Because f of 0 does not exist. So it fails step 1, right? It fails step 1. So for most of these types of problems, we're going to have piecewise functions, right? So let me look at a particular function from the book. And so I'm looking at section 2.4, okay? I like the problems here. I like problems 14 through 18. That's where you're showing things are discontinuous. So 2.4, number 14 to 18. I like problems 31, 32. Well, and some of those 31 to 37, right? And so some of those will be actually for your written homework for not this Monday coming up, but the following Monday, right? Cool, so let's do a problem here. Am I right? I did start talking about this on Monday, did I? I started talking.
Yes, all those so far we've covered.
Yeah. Okay, so this is number 16. So 2.4, number 16, and I want to show that a particular function is discontinuous. Now, there's a lot of piecewise functions in this section, and you should have done a lot of piecewise functions in pre-cal, and you probably hate them as much as I hated them. But don't be a hater. Let's get over it, right? So piecewise function, I have a two-piece function here, x squared minus x over x squared minus 1, when x does not equal 1, and when x equals 1, I have a height of 1. So obviously I'm interested in, is this thing continuous at 1? That's where I'm interested, right? Now remember, I'll just do a quick little comment here. This is the f of x here, right? And this is the domain, right? So the first thing is my function and the domain of that function. Then the next part of the function and the domain of that function. Now I like to use Desmos on when I'm graphing these, but you should also look at how to graph a piecewise function on a TI-83 or 84, whatever you have. Now this one's a little bit weird because I can't see well, first of all, notice if in the first machine, the first function there, the top function, if I plug in 1, I get 0 over 0, right? So there's my indeterminate form there, right? So I can't really show this too well on Desmos, but I'll do my best here. So I've got y equals x squared minus x all divided by x squared minus 1. So I can't really see the hole at 0, 0, but I know there is one. Right? So I know there's a hole at 0, 0. Is that clear to everybody that that's an empty hole, right? I could fall in there, right? And what's the manhole cover there? I like to think of this as me lifting off the manhole cover there. Look at the function. When x is 1, the height of is 1, right? So I should have a point at, oh, sorry, 1, not 1. Sorry, not 0, 0. I'm lost. Oh, yeah. I'm not interested in at 0. I'm interested in at 1, right? So I'm going to put in x equals 1. There is also a way to graph a vertical line on your TI-83s. Again, do a Google search, and then they want the point 1, 1, right? Is that clear? So you can see that manhole cover. It looks like there should be a hole at 1, 1/2, right? You with me there? 1, 1/2. So that green is actually a hole, right? And so a manhole cover, and I took it off and moved it up, right? So clearly not continuous, right? So, but we want to show where our 3-step process fails. Yes? And I told you this stuff is boring. It is boring. Sorry. I can't help it. I get bored so easily. You can tell by the plank look on my face when I'm bored. It's a joke. So plank look. So what's my first step, right? Find f of 1. What is it? Do I use the first machine or do I use the second machine? Do I use y1 or do I use y2?
Y2.
y2. So f of 1 is 1, right? Second step, find the limit, right? The limit as x goes to 1 of y1, right? Yes? And so I can see that that's,
Yep.
I can factor that, right? So I get an x times an x minus 1, and then I get an x plus 1 times an x minus 1. Don't let me go too fast there. Is everybody okay with that? And so I see my x minus 1's cancel. And now I can plug in. I get 1 over 1 plus 1. There it is, my 1/2. Again, notice when I plug in, I'm not still writing limit, right? I'm already there. So this one exists, right? Check. This one exists, right? Check. But guess what? They don't match, right? Since the limit does not equal f of 1, f is discontinuous at 1. Yeah, that's step 3. You know, and when you do one of these, nice little summary is good to put on the paper, right? If you're kind of taking a test and you go, oh, so it's discontinuous. Oh, it's discontinuous. You want to, don't keep that thought in your head. Put it on the paper. It's discontinuous because they didn't match, right? You want to communicate as much as you can on the paper when you turn it into me. So pretty easy, right? Pretty simple. So let's move to the more difficult problem, unless you want me to do another one like that. Okay, so let's move on to the typical problems that I'll give you. This one where I'm going to try and make things continuous, right? So you want to kind of create a continuous function. We'll do a nice simple one, and then one a little bit slightly more difficult, and then make sure you do all of the ones on my old tests, right? So let's say our function is a three-piece function. Well, that's a bad curly bracket. Yeah, there we go. Let's say it's equal to 1 for x greater than or equal to 2. It's equal to ax plus b from -1 to 2. And it's equal to -1 for x less than -1. So 3 pieces, right? The first piece and the last piece are horizontal lines, right? And the middle piece is going to be a diagonal connecting, making everything continuous, right? This one's pretty simple to draw, and I would say if you're confused, try and put the graph down. The graph will help you, right? So 1, 1, 2. I know at 2 and higher, I've got a height of 1, and that manhole cover is on the road, right? That's filled in. You can't fall through there. From -1 and left, it's open, and then at a height of -1. So there's a hole there, right? I'm trying to fill in with this line, right? I'm trying to fill in with this line, but I really just want this piece of it, right? I just really want this piece in green that fills in that hole and wraps around the other point, right? You with me there? So this one is y1, this one is y3, right? And this green one is y2, that middle piece. And so I need to find A and B, so that's what the question will be. Find A and B such that f is continuous everywhere. Find A and B, find real numbers A and B, such that f is continuous for all x's. And of course, the two x's I'm interested in are 2 and -1, right? Nice, so there's 2 ways to do this problem. I would always choose the easy way when I'm trying to find a line. I just want to find the 2 endpoints, and then I can get the line, right? Or sometimes, if the function connecting is not a line, I might have to do some more work. So I'm going to do one first the easy way, and I'm going to do a different one with a little bit more of a tricky notation. So I already know that these 2 points, this one's 2, 1, and this one is -1, -1, right? Everybody with me there? So I'm just trying to find the slope, and I'm trying to find the y-intercept, right? So first of all, I know the slope, right, which is really the value of a, right, ax plus b, right, is 1 minus a -1 all over 2 minus a -1. So it looks like 2/3. Yeah, we're okay here. Now I want to find the b value. The quickest way to find the b value is just get the equation of the line, right? So y minus 1 equals 2/3 all times x minus 2, right? I'm using that point without the negatives, right? so I want to simplify this. Try and make it look like an mx plus b. And it looks like I get 2/3 x minus minus 1/3. Right? Let's someone double check me there. Finish your line and then make sure we get the same thing. Noel and Jesse T lost your cameras. Anybody else get a b value there of negative 1/3? Yes, thank you, Caitlin. Now, of course, I want to graph these. I'm going to have only my TI, whatever I have, right? Does everybody have a TI 83 or 84? Anybody not have one? If you don't have one, you can borrow one from the school, right?
Sir, I have a different one.
What do you have? What do you have? TI 89?
No, it's like a Casio G2, something like that.
Oh yeah, you can't use that one. It does derivatives for you.
Okay, so where do I get the calculator?
Where do you live? Close to which campus?
At Tacoma Park.
Okay, so in the Math Pavilion, there's the Math Learning Center, Math Science Learning Center. So you can go in there, just show an ID, and they'll let you borrow a calculator for the semester. Okay. So we're going to graph this in a second, but let's assume it's right. And I want to say with a equal 2/3 and b equal minus 1/3, f of x is continuous everywhere. And the writing is it sucks. But wait do you see chapter 4. If you think the writing is going to suck now when you make a conclusion, wait do you see chapter 4. Oh my god. Oh, it's hideous. I mean, I'm a realist, right? Life sucks. Learn to deal with it, and everything will be all better. All right, let's graph this so I can at least show you how to do it on Desmos. Okay. I'm just showing on Desmos. It's so hard to see everything on the calculator on the screen, but make sure you do it on your calculator. I really think that you can leave this task knowing you got everything right. Right? All the limits can be checked numerically. All the derivatives can be checked with continuity is a limit, really, so that can be checked with a graph. The derivatives can be checked with a graph, right? You're doing a tangent line. What else is on there? Not much. Not much else on this first task. So anyway, I had y equals -1. And watch how I restrict curly brackets for x less than -1. And so there it is. So you can see, and it's not clear that there's a hole at -1, right? -1, -1. It's not clear from the graph, but there's no way to, to make it any clearer. Let me see if I can put in -1, comma -1, and then color it. Maybe I can color it white. No, I can't. So there's no way for me to show that there's like that empty circle there. We got our other piece of y equals 1, right, for x is greater than or equal to 2. The greater than or equal to is not that important, but it is here in that little menu. And on that one, I do have a point at 2, 1. So that one I would say I could put there. Again, graphing a point on the TI-8384 will involve a stat menu, and it's a little complicated, but it's all on the web. Not that you have to do it, right? I think the piecewise is more important. Now I want to see if that piece that I had matched up, right? So what was it? Y equals, I forget, 2/3? 2/3 x minus 1/3. And I'm restricting between -1 less than x. I don't care about the less than equal because I can't see that detail anyway. And there it is. So it's connecting. Right, and I guess that green line gave me the yes, Epson.
I know you said you don't care about it here because you can't see it, but like on the exam, because the like y equals -1 had a like a hole.
Yeah. You would probably you would probably draw it like I drew it, where where is it? I can't get it. You see where my y3 curve has got a hole in it, but then the y2 curve filled in the hole.
Okay, redraw it like that, and then if you wrote down the, oh yeah, it's right there.
Yeah.
Thank you.
Oh, Professor, you said you couldn't find a way to make a hole on Desmos, right? There is a possible way. And,
Tell me.
so if you go back to Desmos,
Mm-hmm.
and if you were to click where you're gonna change the color of the of the point,
Yep. Mm-hmm.
and then you click to go to change the color.
Yep. Oh, there's the hole.
It's right there.
Oh, no, thank you. I get excited about stupid. I'm a nerd. Can't help it. So I wanted that whole purple, right? So -1, comma -1. And then I want to change color, right? I want it purple and I want a hole. And then I don't know if I put another point in green, I can, but I don't think I think it will cover the purple. But anyway, I'm just nerding out here. And so now, because I want that green, let's see what it does. It covers it. You can kind of see the purple. You can see it's a little darker there, but who cares? It's just me being. Now, here's my question. Does the limit exist at 2 for this function? Obvious, because we already know it's continuous. Is it continuous at 2? Obvious, right?
Yeah.
Is it differentiable at 2? Well,
No.
First question should be, what the hell does it mean to be differentiable? It means I can find the derivative. But what is the derivative?
It's piecewise, so you can't.
No,
Unless you only look at one part.
wait for me. What's the derivative? What is the derivative? What does it do?
Tell you the slope of the function.
A slope at a single
get a
point. A slope at a single point. But I'm going to kind of take this point at 2 and rotate it a little bit, just to pretend. So there's my point at 2, and here I am on my skis, right? I got my music on. I'm on my skis, I'm on that point, but can you see me kind of like trying to keep my balance? Right? So the skis are shaking, yes? Right? You see what I'm saying? I'm trying to balance on that point. So is my slope from the left the same as the slope from the right? No. So the derivative doesn't exist at that point. So not differentiable. Right? That's a deep thought, so don't worry about it too much, okay? So, but differentiability, this is a thought I really want us to think about. If I can take a derivative, if the function's diff, then it has to be continuous. I have to be able to stand on the point of the hill, right, to measure the slope of my skis, right? Is everybody comfortable with this thing about me skiing in the snow, Winter Olympics kind of thing? Everybody understands this? I don't want to, right?
So it's differentiable when so basically like r minus and r plus are the same, so on both sides.
Exactly. When the derivative, right? When the derivative is the same left and right. In fact, if we look at that function, right? If we look at that function, what y1 was 1, right? What's y1 prime? 0, right? So the slope to the right of that is 0. Obviously, it's a horizontal line. And y2, we got 2/3 x minus 1/3. What's y sub 2 prime? 2/3, right? Well, clearly 2/3 doesn't equal 0. So not differentiable there. Yeah, everybody okay here? So differentiability implies continuity. I can't measure the slope of my skis on the hill unless I can stand on the hill. And continuity implies there's a limit. Right? And it doesn't work the other way. If I have a limit, doesn't mean I have continuity. If I have continuity, doesn't mean I have differentiability. All right, let's do one more and then quit for today. Sound good? Sounds good to me. Breakfast time.
So we found the answer. The answer was it was continuous on those points of A and B.
Yes. Yep, exactly. And we checked it with our calculator, right? And of course, like I could draw the worst case scenario, right? Worst case scenario is you're drawing the first function, but you're drawing the whole thing. Right? I'm sorry, the first one was up here, right? Right. So you're drawing the first thing, but you're on your calculator drawing them both, and then you're drawing that line, and you should be able to see, even if you don't do the piecewise part. But it's not that difficult on TI-83. I think in Y1 you put 1, and then you multiply it by x greater than 2, something stupid like that. Just look it up. Just do a quick Google search on how to draw a piecewise function on the TI. Okay. Okay, let's do one more problem and then quit. So this one is coming from my Chapter 2 test from fall 2019. So I'm going to open it in a different window, but it's there in that folder, right? So just because it's easier for me to not, I'll write the problem down, okay? Past exams, Chapter 2, everything's so slow, I can't stand it. Fall 2019. So this is from fall 2019, number 10. I think there's 11 questions on it, and I'm planning on 10 questions for you, maybe an extra credit. The extra credit on this particular one was a epsilon delta. I'm not going to do that, no. So here's my function. I want to find, so this is a fall 2019 Chapter 2 test. Number 10. So I've got a function. It's a two-piece function. I've got a linear piece. Oh, look at that, between -1 and 2. And I've got a quadratic. I got an x squared curve everywhere else. Right? We want to find A and B. So f is continuous. All right, so everybody's kind of with me here. I can do a quick sketch of this, and then I'll show you how I cheat. I'll show you how I cheat the piecewise. I already know. The graph that I know is y2, right? It's an x squared. And at -1, I hit a height of 1. And then at 2, I hit a height of 4. Right? And I can see this quadratic. Let me try and do a rough sketch of it first. Right? But it's pretty clear that it's open at each point, and it's only the rest of it. It's only the quadratic piece that's outside of the range of -1 to 2. Yes, you with me there? So without a calculator, I can sketch this. It wouldn't be a surprise if when I give you on your test, you can sketch easily without going to the calculator. And look at what I want. I want to connect, right? I want to connect with this green, filling in from here to here. Right? Is that clear? So that's y1 in green, and then y2 is in red. Now look at the differentiability at those points. No way, right? The slopes are crazy different. The nice way to think of a differentiable is a smooth curve, a kiddie ride, right? Anytime you have a nice smooth curve, everything flows. That's something differentiable. So I want to do this one differently, okay? Because I could give you something where you can't just pick the endpoints and then get the answer, right? So I want to do this as if I'm setting up a system of equations, okay? So I want to do two problems. I want to do a problem at x equals 2, right? And then the same problem at x equals -1 and see what my results are. So I'm looking at that continuity piece, right? What is f of 2? Well, I've got to use my green function, right? So I'm plugging in 2 into the green function. That's where I can, right? So I get 2a plus b. Is that agreed upon? But I want to, so that's for the green. For the limit, I'm going to use the x squared function, right? For the limit, I'm using the x squared function. Is that, yes, you with me? Let me rewrite this as green, ax plus b, right? And then red is my x squared. So I have to also do my limit as x goes to 2 of my x squared function, right? But that's obvious. That's 4, right? So what do I get from these two things to be continuous? I must get that 4 is equal to 2a plus b. Make sure you're with me there. Make sure you're comfortable here. Now, on this particular function, on this particular problem, I could use the method I already used. But I'm saying to you, I could give you a problem where you can't use that method. So I want you to be comfortable with both of these, okay? Now I've got to repeat this process at x equals -1. When I find the function, again, I'm using the green function, and that's going to give me what? -a plus b. Right? Step 1, find the value of the function, find the height of the function at that point, right? And then step 2, find the limit. So I need the limit as x goes to -1 of x squared, and that's obviously 1. So both of these are telling me they have to match up, right? That's my third step in continuity. So I know that -1 has to equal -a plus b. And what I end up doing is creating a system of equations. And I don't know if you remember this from Algebra 1 or maybe even Algebra 2. You could have had them in pre-cal. So I'm either using substitution method or elimination method, right? You remember all of that fun time you had? Everything we've been doing to you, all this torture. Go ahead, Nahum.
Yeah, so it's supposed to be 1, not -1.
Thank you. Thank you. My teachers would always say, "Oh, I made that mistake on purpose to see if you're paying attention." But guess what I was thinking about? I was thinking about the slope, right? I was thinking about that negative a, and I put the negative. So that's when we make mistakes. We start rushing ahead. We start thinking about the next thing I'm going to do instead of finishing where I'm at, right? Same reason why most car accidents happen close to home, because you're starting to think about, oh, what's for dinner, instead of driving. Or did the dog pee all over the place? So now I have a system, and I'm going to solve the system. I'm going to really be close on time here. I only have like a little bit more than 4 minutes. But I've got a system of 4 equals 2a plus b and 1 equals minus a plus b. I'm going to multiply everything here by 2. I'm going to do elimination method. So 4 equals 2a plus b and 2 equals negative 2a plus 2b. And now if I add them, right, my values of a go away. I get 6 equals 3b, so b equals 2. And obviously, it looks pretty much on my graph like the line's going through 2, right? And then so we get a equals 1. So 4 equals 2 times a plus 2. So 2 equals 2a, so a is 1. Etc., etc. Conclusion, we're out of time. Have a great Wednesday. See you Friday.
Hey, Professor.
Thanks, Professor.
Have a good day.
Thank you.
Thank you, Professor.
Hey, Professor, bye, everyone.
I have a dumb question.
Sure.
Sorry, what's the office hours again? I don't see it on the syllabus. I'll sort out how to find that.
Yeah, that's right on the syllabus. Let me stop my recording and then I'll show you.